Vector Calculus 1 Field Function. Okay, so vector calculus is a college math, and the calculus itself is in high school. You learn calculus, and you may learn, if you take a AP class, multivariable calculus too. So the story starts from there. First of all, we need to understand why this kind of things come up in the math. The demands always come from physics. Okay, well, math sometimes work itself alone and find out later that it's useful for something, but a lot of demands come from physics and science, and that's advanced math. So let's review a little bit why Newton's motion, how it's described. Okay, we have a vector x, y, z that shows a position, location, and the x is a function of t, y, and z. So we write it this way: vector position vector r is a function of t. Okay, so this is not the multi-variables, it's single variable, but you have a multi function x, y, z. They are all function of t. But when you say trajectory, then it's become a curve in the space, how the motion moves. Okay, in two-dimensional y equals fx, the three-dimensional z equals fxy. So it's a multi-parameter, multi-variable function. So if you want to know how much the height of the location change, you take a partial derivative of x dx and partial derivative by y dy. And what this is suppose you have x, y, z, and you have a curve. This shows trajectory. Say take one of curve. Okay, but it's if this curve is parallel to y, then it shows for dy how much height change, dz. But actually it's affected by x too. So if you take a dx, then it shows how much dz change. So both of change affect dz, because you may be moving this way projectly, right? So this kind of function is a multi-variable function. Okay, now this is the first time the multi-variable functions used in the Newton's physics. But now Newton's method is not sufficient to describe things like fluid movement. The Lagrange tried it, and it is very difficult. So we need to introduce something else. And besides the motion, there is a physical things like a density function. Okay, like typically gas star has a gravity, and it's very dense inside, and the less dense it goes like that. And depend on distance, density change. And r is xyz. The potential field, the gravity, same thing. The potential gravity is very strong near planet, right? And potential field spread in the space by gravity this way. Okay, so this is the multivariable scalar function. The another one is it came from the fluid dynamics originally. What happened is the try to track the fluid movement in this kind of problem is very complicated. Okay, this S is a source, means the water coming out, and E is drain, and you may have another source. So water moves this way, and suppose we are in a steady state. That means it's constantly flowing, and the flowing pattern doesn't change over time. So the water is flowing according to this line. This line is called flux, right? And you draw the flux. The Euler is a genius. He figured out what we need to know in this kind of problem is not the movement of each mass, instead location, the speed at each location of the flux. So each location of flux speed is different, and if we know this, if we get this information, then we know pretty much about the steady state of the fluid movement. It's just they calculate the speed times mass density, take integral over time, then you know the quantity of flowing stuff. Okay, so this approach was taken and successfully made the famous equation called Bernoulli's equation, which is the basically velocity at each location. This is each location and the velocity. So this is a vector function, the multivariable vector function. Those potential field is a scalar function, right? But it's vector. Vector can be also multivariable. In fact, there are many like that. Electrical field and magnetic field, they are all vector function, but it depends on the location. So how do we handle this kind of function? And that's a math developed here. It's called field function and calculus. That means we have to be able to take a differentiation. And how can we take a differentiation? It's continuity, and continuity is a flux. So we track the movement of mass, so it's continued, and the mass doesn't suddenly disappear here. The mass disappear only in drain, right? And the source, its mass appear. Okay, so it's a continuity. And smooth curve, that means if it's hit the block, something like that, then it may split into two locations. And this part is a singular point we have to avoid for differentiation. It's not smooth. And single function value, this has a two velocity on the right and left, and so this part is not differentiable, right? So we have to avoid those areas. And what we do is we get this function, and you need to know acceleration by taking derivative, and the integration, and probably density to get the volume. Okay, so we need to be able to take a get the calculus over this kind of function, and that's what it's about. Next two video shows how to do this. Okay, and that's the vector calculus. Now, when you have a function f, for example, f xt, yt, and zt, this kind of functions, when you take a derivative by t, then you take a partial derivatives and take a derivative of x over t, and you repeat for y and z. So this is a kind of review of multivariable or multi-parameters calculus, right? Now we have a vector. The vector is broken into I, j, k vectors. Okay, we cover this in the vector algebra. Okay, so basically it's we have three functions, and for example, each one can be function of x, y, z. But if ax is function of only x, we can simplify to this form, right? Okay, now there are many assumptions here. You have to pay attention. The for example, some value is a vector value. It's pointing somewhere, okay, and you take a derivative over x, and this x could be function of only t or y, z, t. You never know, okay? And when it's come to this I itself is a function of location, then it's become tensor. Okay, so mathematics explode from all kind of cases from here. Okay, but basically what we have here is, say you have some kind of curve and you take x, y, z direction, and you want to know the here vector, say vector is v, how much vector value change including direction. Okay, it's going to be and this vector dy, so you know this derivative is the rate of change on each direction multiplied by the quantity of x, dx and dy and dz is going to give total change, and the v can be a set of number. Complicated? Well, yeah, but you deal with each physics case, then you can simplify and equation will be not that complicated. The most complicated is like tensor. It's everything changes, and that's happened when the space is curved and you're getting into a general theory of relativity. When space is curved, this I, j, k is not constant. Okay, so every operation becomes like a matrix. But that's another story. That itself is another the math course you have to take if your major is physics. Some engineering, like analysis of elastic material and stuff, they get into this because inside the material bend, and the force inside is depend on the location, but this location itself is a function of this bending. So the curved space, general theory of relativity, or those engineering problem, it's become necessary to deal with it. But for the classical physics, the pretty much it's simplified. So only key calculus formula you have to learn is going to be in the next 2 video. Okay, so you can go on and continue on to the next video, the vector calculus 2 and 3. If you like this, please hit subscribe.